Welcome to the fourth lecture of this week. Today we will start about discussing about energy or virtual work based approach for buckling analysis. We have seen previously that Levy type solution or Navier type solution is not always possible. So, we need something which can be applicable to most of the cases. So, for that we have the energy based approach or the virtual work based approach. Now let us again consider a problem like this. We have this laminated composite plate and that is under axial load, distributed axial load or uniformly distributed axial load across both the edges. And this is our axis x, this is axis y and this is axis z. And also apart from these axial forces, there are shear also. So, this we can call the axial force along direction wall, let us call it Kx multiplied by n bar, and axial force along direction y, let us call it n bar multiplied by Ky, and the shear force is Ks multiplied by n bar. So, n bar is common and then we multiply it with different factors and we get the different loads. So, that is how we represent the biaxial compressive load and the shear load. So, our goal is to find out these values of the so this Ks, Kx, Ks and Ky are known to us. So, Kx, Ky, Ks are known. So, we need to find out n bar which causes buckling, and if we know n bar we can find out the compressive force, the shear force and the both the compressive force and the shear force. For example, here if K is equal to 0, that corresponds to a purely biaxial load, biaxial compressive load. If Ks and Ky both are 0, it denotes only uniaxial compression along direction x, and if everything is present, it is a combined case where everything is present. If Ks is only non-zero and rest of them are 0, then it is a pure shear case. Now, this is how we write the energy equation. So, we know that in our total potential energy expression we have one part that signifies the strain energy, total strain energy, and the other part is the potential applied load, which potential of the applied load, and that is negative of the work done by the applied load. So, we have pi is equal to total potential energy, pi is equal to total potential energy and that we represent as U minus W, and minus W we can call generally V, that means potential of the applied load. So, here this represents U for this case. So, we have half into stress into strain and there are 3 non-zero stresses, and so we have we just sum it up. So, there are this is the total strain energy, and this is our W, the work done by the external load. So, this is the compressive load, and when I multiply the compressive load with this, I get the work done by the compressive load. Now, this can be proved how this expression comes, but we are not going to the proof now. So, let us proceed from here. Now, if I take this delta inside, then I can write the U as this, delta of U as this. So, stress multiplied by the variation of strain, and we do it for all the 3 components. So, that is the internal virtual work, and then we take this delta inside here and we can write it like this using the property of the variational operator which we discussed before. And we can also do integration by parts here, and we can shift derivatives, this derivative to this derivative, and then it will become delta w del 2 w by del x2, and this will become a variation of w, and that signifies the external virtual work, but we are not doing it. We will keep it as it is, and then we will proceed from here. Now, let us write the strengths into in terms of its components. So, we know that epsilon x is epsilon x 0 plus z multiplied by kappa x, and likewise we know that epsilon y is equal to epsilon y 0 plus z multiplied by kappa y, and we know that epsilon s is equal to epsilon s 0 plus z multiplied by kappa s. So, we have replaced epsilon x, epsilon y and epsilon s in terms of their definition, in terms of epsilon x 0, y 0, s 0, and kappa x, kappa y, kappa x, kappa y and kappa s. And also if we see this expression, here the first term is the volume integral, and these are the surface integrals. Similarly, this is the volume integral and these are the integral over the surface. So, this x ranges from 0 to a and y ranges from 0 to b. So, what we do is we convert these integrals, these volume integrals into a surface integral, and for that we need to first integrate with respect to the thickness, and then rest of it is expressed in terms of surface integral. Now, we know that across the thickness sigma x is not continuous. So, what we do is we integrate over each ply and then we sum it over all the plies, and again we have discussed before that in a composite laminate this is Z0, this is Z1, and it goes on up to Zn. So, for kth laminate the range of z coordinate is zk minus 1 to zk, and that is what we see here, and then we sum it up over all the plies. So, now everything is converted into a surface integral. Now, one thing to note is previously we wrote the surface integrals as an integral over omega. So, that was a more generic definition of the surface integral, whatever shape the surface has we could represent it like this, and here we have written in terms of integrals from x equal to 0 to a and y equal to 0 to b. That is a more specific case. So, that is specifically for a rectangular surface which ranges from 0 to a along x and 0 to b along y. So, I can say that this is a specific case of this. Now, we know that if I integrate sigma x over the thickness of each ply and sum it over, we get nx. We have discussed this before, and similarly we have sigma x multiplied by z, and if I integrate that sigma x multiplied by z over the thickness and sum it up, we get mx, and likewise from sigma y integral of that we get ny, and integral of sigma y into z we get my, and integral of sigma s we get ns, and integral of from integral of sigma s into z we get my. And also this kappa as per definition is minus del 2 w by del x2. So, a negative sign comes here. So, that is why the negative sign is here. Similarly, here also the same thing, and kappa s is also minus 2 into del 2 w by del x2. So, we can see a negative sign here, and this term is written as it is. Now, what we do is we need to make some approximations for u0, v0 and w, and put the approximation in this expression. So, the approximations are, so these are the approximations. The approximations are u0 as a function of x y is summation I from 1 to L, then phi uy which is a defined function for of x and y multiplied by a uy which is a unknown constant. Similarly, V0 is also written as a weighted summation of these 5 V's, where 5 V's are known to us, defined function of x and y, and the weights are these unknown constants. And likewise we do for W. So, here we have phi Wi and AWI. Now, if I want to take a variation of these quantities, so if I take variation of U0, so delta U0, now this quantity phi Ui is known to us, so I cannot vary it. This is unknown to us, so the variation if I take variation, it becomes summation I from 1 to L phi Ui multiplied by variation of AUI. Similarly, if I vary V0, delta V0, I get phi Vi and multiplied by variation of Vi. Likewise, if I vary W, so delta W, variation of W, I get phi Wi multiplied by variation of AWI. Now, let us look into the derivatives. So, we have, let us take del U0 by del x, and we can write this as I equal to 1 to L. If I look into this expression, AUI is not a function of x. So, AUI remains as it is, and phi Ui being a function of x, we can differentiate with respect to x, and then we have AUI. AUI. Now, if I want to take a variation, I can take it, and then again this quantity cannot be varied. So, we have a variation of AUI here. Likewise, we can write variation of del U0 by del y, and that can be written as I equal to 1 to L delta derivative of phi Ui with respect to y multiplied by variation of AUI. Similarly, let us do it for del V0 by del x, and that we can write as I equal to 1 to m multiplied by phi Vi del phi Vi by del x into variation of AVI multiplied by variation of del V0 by del y into summation of I equal to 1 to m multiplied by del Vi by del y into del AVI. Now, let us look into W's. So, we have, let us take a second order derivative of first order derivative of W. We can define del W by del x as I equal to 1 to n multiplied by del phi W by del x into variation of into AWI, and if I take variation, then we have variation here also. Similarly, we can do variation of del W by del y, we can write this as I equal to 1 to n del phi W by del y multiplied by delta AWI. If I take second order derivative, which is there in the expression, energy expression we have seen, we can do the same thing, only thing is that phi Wi is differentiated twice. Then we have variation of del W by del 2 W by del y 2, and we can write I going from 1 to n del 2 phi Wi by del y 2, then variation of AWI, and we can take a mixed derivative del 2 W by del x del y, and this we can write as summation 1 going from I going from 1 to n del 2 phi w by del x del y and then variation of a w I. And one thing to note is that we have not taken same number of terms for u0, v0 and w. For u0 we have L number of terms, for v0 we have m number of terms, for w we have n number of terms. Now that is our choice, we can choose them to be same also, we can choose L equal to m equal to n, or we can make different approximations. Now if I put everything in this expression, we can express this entire quantity, as functions of AUI, VUI and AWI, and we will have their variations also. So let us do that. So first let us write this quantity in terms of the approximations that we have made so far. So we have, so putting these approximations, if I call it equation 1, so putting these approximations in equation 1, we can write the first term was integral 0 to b 0 to a, and then we have nx. So yes, we have nx into del u0 by del x. So let us write nx multiplied by summation I j is equal to 1 to L del phi ui by del x multiplied by variation of AUI, and then we have mx. So mx, and that is multiplied by del 2 w by del x 2. So we have summation I going from 1 to n multiplied by del 2 phi w I by del x 2 into variation of A w I. Then we have plus ny. So plus ny multiplied by del v0 by del y. Just one correction here, this index should go from I equal to 1. Now here we have ny into del v0 by del y. So again the index going from I to I equal to 1 to m, not n. I equal to 1 to m, then we have del phi v I by del y multiplied by variation of A v I, and then we have my multiplied by del 2 w by del y 2. So here it goes from I equal to 1 to n, then del 2 phi w by del y 2 into variation of AWI. Now we have NS, the shear. So NS, and this has two terms, del u by del y plus del v by del x. So let us put it in the bracket, I equal to 1 to L. So let us deal with del ui by del y first. So del phi ui by del y multiplied by variation of AUI, plus we have I going from 1 to m and del phi vi by del x multiplied by variation of AVI, and then we have ms, and for that we have plus 2 minus 2, not plus, minus 2 ms multiplied by del to w by del x del y. So, we have I going from 1 to n and the mixed derivative del to phi w I by del x del y, and then we have variation of a w I. So, if I look at these terms, we have dealt with this, we have dealt with this one is done, this one is done, we have dealt with this one and this one. Now, we have to take care of these terms. So, here we have del w by del x and variation of del w by del x, and the sign is minus here. So, minus n bar into kx, then we have del w by del x. So, summation j going from 1 to L del phi u I by del x into a u I multiplied by I equal to 1 to L, then del phi u I by del x multiplied by variation of a u I. Now, here let us understand this, that here we have del w by del x and here we have variation of del w by del x. Now, when we put the approximation in this, where the variation is not appearing, we are writing the index from j is equal to 1 to L, and where variation is appearing, we are writing from I equal to 1 to L. This is just to differentiate that. I could have written I equal to 1 to L, 1 to L here also, not a problem. Now, we have minus ky n bar into del w by del y multiplied by variation of del w by del y. So, for that again j is equal to 1 to m, then derivative of V I with respect to y, a V I multiplied by I equal to 1 to m into this is del j, because we have used the index j here, multiplied by del V I into del y into variation of a V I. Next term is we have k s n bar multiplied by del w by del x and variation of del w by del y. So, now we have k s n bar. First, let us take care of del w by del x. So, j is equal to 1 to okay, just one correction, these things were variations of del w by del x. So, I should not put u here, rather these are all v's and w's, and everything goes up from 1 to n. So, it is j is equal to 1 to n wi, and this is also wi. Similarly, I equal to 1 to n wi, and this quantity is also del w. So, everything has w, not u or v, a w I. Similarly, w j, a w j, a w I. So, these are all derivatives of w, not u or u0 or v0. Now, we have ks into n bar. So, j going from 1 to again n, we have del w. So, these are all yes. So, this is j. Now, we have del wj by del x multiplied by a wj, and then we have variation of del w by del y. So, I equal to 1 to n multiplied by del wi by del y into variation of a wi. In the next term, it is the other way, the variation is there in del w by del x. So, minus ks into n bar, j going from 1 to n derivative of phi wj with respect to y multiplied by a wj into I going from 1 to n del wi by del x into variation of a wi. So, these are all the terms and everything is integrated from y equal to 0 to b to x equal to 0 to a. Now, our job is to separate out the terms which has variation of AUI and then the terms which has variation of AVI and also the terms which has variation of AWI. So, if I look at this term has variation of AUI and then we have this term with variation of AUI. So, they have to be separated out. Similarly, this term has variation of AVI and this term has variation of AVI. So, they have to be separated and rest all have variation of AWI. So, if I do that finally the expression after separating out what I get is this. So, we have variation of AUI separated out, variation of AVI separated out and rest all these terms has variation of AWI. Now, we make the same argument that all these variations are independent variation and arbitrary variation. That means that anything I multiply with that variation should be separately 0. So, variation of AUI is equal to 0, I mean the coefficient of the variation of AUI equal to 0, that gives me L number of equations. The coefficient of the variation of AVI is 0, that gives me M number of equations and the coefficient of the variation of AWI is 0, that gives me N number of equations. So, here we get that. So, these are the equations that I get. So, here if I set out okay. So, here it is written vice versa. This has to be this is actually the first equation that I get. This is obtained from the set by setting out the variation of A Vi equal to 0. If I look at this here, so if I set the variation of AVI and if I set the coefficient equal to 0, then I get this term ny into this plus this and that gives me one equation and this is this equation. So, this gives me total m number of equations. Then we have variation of AUY equal to 0 and that gives me total L number of equations and these are the equations. Again if I look at it here, I get this multiplied by this. Yes, and then for rest of the term the equation that I get is this. So, I have total L plus M plus N equations and from that system of equation we have to solve for N bar and that will give us the buckling loads. Now, if I arrange these equations in a matrix form. So, before that when B matrix is 0, that means the laminate is symmetric. In that case these two equations are uncoupled from this equation. If I look at the expressions in mx term I have B arising, in nx ny I have B arising. So, if B is 0 that means the coupling is not present, we have seen that before also in static analysis. So, if B matrix is non-zero, that means if any of the element of B matrix is non-zero, that means if the laminate not symmetric then we get a system of equations of size L plus M plus N equations. And those equations can be written in this form: L by L, B L by M, C of size L by N, and then we have B matrix transpose of that. Then we have a D matrix, this is M by M, and C D E F E, and that is M by N. Here we have transpose of C matrix, here we have transpose of E matrix, and here we have F matrix of size n by n minus n bar into a matrix of size let us call it G of size n by n, and everything multiplied by a vector of these UMNs, or let us call it a vector of just U. So, we wrote them as AU and AV and AW. So, those unknown coefficients. So, AU, AV and AW, and this gives equal to this gives us 0. Now, in this problem as we know that a trivial solution is AU, AV and AW is 0, but that trivial solution we do not want, that will not give us buckling. So, for a non-trivial solution to exist, the determinant of this should be 0. Now, if I set the determinant this equal to 0, I can solve for n bar, and those n bars are the buckling loads. So, I will get total capital N number of these n bars, and those are capital N number of buckling loads. And then if I put each capital N here, and then I can solve for this, and I can find out AU, AV and AW, that will give us the buckling modes. So, let us, if I call this matrix as, let us give it a name, let us call it P matrix. So, determinant of P is equal to 0 will give us the values of N, that means buckling loads. And substitution of each N let us call it equation number 2 yields buckling modes, yield buckling mode, corresponding buckling mode. Now, one thing to notice is if our choice of the basis functions, that means this phi ui, phi v I, phi wi are such that while evaluating these matrices I get the orthogonality property, that means A11 is non-zero, but A12 becomes 0, or I mean Aij becomes 0 for when I and j are not equal. Similarly, Dij becomes 0 when when I or j are not equal, and likewise this Bij, Cij becomes 0. So, if I get that orthogonality property, then each of these equations become uncoupled. So, for each I can, instead of getting a matrix, I get an equation here. For each I get a 3 by 3 equation, and so I can find out each buckling mode separately in an uncoupled way. But if they are coupled, I have to have this L plus M plus N system and then solve it. And if B matrix is 0, that means laminate symmetric in that case I can separately solve the third equation, then I do not need to have the first equations. So, if I separately solve the third equation, I get F minus n bar into G, or I can write it separately also. So, let us separately multiply the W bar, the W here, I mean AW here. So, I get a equation of this form, F into vector of AW minus n bar into G into vector of AW. So, this is n by n, this is n by 1, this is n by n, and this is n by 1, that is equal to 0. So, it is an eigenvalue problem and I can solve it, and the eigenvalues comes out to be the buckling loads and the corresponding eigenvectors comes out to be buckling modes. So, in the next class we will see an example of this kind of problem. So, this brings us to the end of this lecture. Thank you.